Most people experience generative AI through chat boxes owned by massive technology companies. You type a prompt into a sleek interface, it pings a server in a vast data center, and a polished output comes back. But interacting with these models purely as a consumer means accepting strict boundaries. You operate within the specific guardrails, styles, and locked parameters set by the host company. Outside of those locked application programming interfaces, there is a sprawling open-source ecosystem. Platforms like Hugging Face host millions of accessible models that anyone can download, modify, and run entirely on their own hardware. This decentralized network relies primarily on two core mathematical frameworks, transformers and diffusion models. By understanding the architecture of how these engines actually process text and imagery, you gain the ability to adapt them. You move from simply accepting whatever the machine hands you to directing exactly how it generates new ideas. At the core of a text engine, like a transformer, is a surprisingly straightforward task, predicting the next piece of a sequence. The model looks at a string of text and calculates the statistical probability of what should come next. To perform this calculation, the text is broken down into subwords or characters. In this animated diagram, you can see how a single word is split and mapped to specific numerical IDs, called tokens, creating a format the machine can compute. Older language models, like recurrent neural networks, processed these tokens one by one in a straight line. By the time they reached the end of a long paragraph, they frequently lost track of the context established at the beginning. Transformers solve this problem using self-attention. As this diagram shows, instead of reading linearly, network lines connect every single token to every other token simultaneously. The model actively weighs the importance of each word against the whole document. Because it analyzes the entire context at once, the machine can distinguish between a barking dog and tree bark. It stops blindly guessing the next word based on immediate proximity and generates text that reflects human-like semantic structure. Image generation requires a different approach. A standard high-resolution image contains millions of individual pixels. Trying to run predictive math on that scale requires massive, expensive computing power. To solve this, researchers use a tool called an autoencoder. An autoencoder consists of two parts: an encoder that compresses data down to its bare essentials, and a decoder that rebuilds it. This animation illustrates compression. The autoencoder squeezes the heavy 3-channel pixel grid into a highly compressed mathematical matrix known as latent space. Here, it stores distinct layers of essential features, abstract concepts like shape edges, texture, or lighting angles. Generating images within this latent space reduces the total data points the computer has to track by a factor of nearly 50. This reduction allows high-quality visual generation to function on standard consumer hardware, rather than requiring a dedicated server farm. With the data compressed, the actual image generation relies on diffusion. In this generated video, you see the forward diffusion process. A clear piece of training data is systematically destroyed by adding layers of static noise. The neural network is then trained to run this process in reverse. It looks at a field of pure static and iteratively subtracts the noise step by step, attempting to hallucinate a clear image back into existence. But a reverse diffusion model sitting in a vacuum doesn't know what it is supposed to be drawing. Without specific instructions, it will just denoise the static into a random, plausible image from its training data. To guide the output, a transformer converts your prompt into mathematical vectors injected directly into the denoising loop. Using cross-attention, the model checks these vectors at every step, forcing the static to arrange into the specific shape described. This synthesis demonstrates that text and image generation are not separate magic tricks, but interacting mathematical engines. The transformer provides the semantic map, and the diffusion loop uses cross-attention to translate those instructions into visual form. Because the mechanics of both transformers and diffusion models are well documented, the massive pre-trained base models released by researchers act as starting points rather than finished products. You can take a base model and subject it to a process called fine-tuning. By feeding it a small, curated dataset of your own, running right on a consumer graphics card, you can teach the model highly specific aesthetic styles or new factual domains. This leads directly to local inference. Once a model is fine-tuned, you can run it completely offline on your personal device. There is no cloud server, no subscription fee, and no data leaving your machine. Operating offline guarantees absolute privacy. It allows you to integrate the model directly into local applications, like coding environments or internal archives, entirely on your terms. The generative AI ecosystem is built on accessible mathematics and open code. By learning to train and tune these underlying engines, you stop renting access to someone else's closed system and take direct ownership of the technology.